Welcome everyone for High Performance Computing, Advanced Scientific Computing. Today we have our lecture 4 on advanced MPI techniques. It nicely connects what we learned in lecture 2, where I said to you, I injected this a little bit early so that you get an exposure to MPI very early in the course, basically for practical assignments that you're now starting with earlier, and then do a little bit of MPI. Now we left a bit out much of the power of MPI, which will come today. And before we understand really the power of MPI, it was a necessary lecture 3 in between to understand a little bit more about domain decomposition. And then also usual terms like speed up, weak scaling, strong scaling, and so on. Hence, we connect now all these couple of lectures together. We will even connect to many core and multi-core again, when we look then on the network and architecture setup of a HPC machine. Admittedly, it's one of the more complexer lectures, right? So, but we connected nicely with a couple of practical lectures coming down the road. So on Monday, Tuesday, and so on, there will be more practical lectures. Hence, let's look a little bit, because it's built on lecture 3, what we had the last time. And the last time was a little bit, again, the idea of domain decomposition. In the end, we do parallel computing to have a big problem solved in a cooperative way among smaller chunks. So the smaller chunks are loaded. It could be very domain specific, how these chunks are basically now considered. We had the example of matrix vector multiplication with GPUs, deep learning inherently, so to speak. That is a sort of domain I want to parallelize, like the color encoding here. Or we had the idea of maybe just have the maximum of an array, right? Where we said, okay, we can chop down this maybe in 4 different parts, have a local maximum. And from all of these local maximums, I determine the global maximum. However, and there was already a nice term we that we learned is load imbalance, right? We saw this looks all nice, but in the end, this max global needs to be done by someone, right? This is a toy example. But if you think about the reality is that all are very busy doing their local maximum, who is taking care of the global maximum? No one. Hence, this idealized representations that you often see in this parallel computing world are a little bit idealized, nice, but don't really capture the essence of really a parallel program sometimes. Mostly because you have certain roles like rank 0, maybe do some specific things. There will be another facet to it today in the lecture 4 when we talk about I/O, right? Many of the things, let's consider you would have a simulation of weather or whatever we do with climate in the earth science simulation here. We have to load the topography. We have to load data first, right? Before we can compute anything and then do all the physics, which is the number crunching. Hence, there needs to be someone, and this someone is now the big question mark. Who is that in all of these big decomposition to load the data, topography, creating the mesh, the net, or the Cartesian, as we will learn today as well, and then start with the real application. Again, a load imbalance. So someone has to do the special role creating this. Or as we will learn today, maybe there's parallel I/O to the rescue, right? There's a specific technique in MPI as well called parallel I/O I will talk about. But these were important terms. So the domain decomposition, it also is not necessarily always that every little block you see in this, also for the online audience here, that doesn't mean necessarily that you have a processor always behind this, right? Even if you have a Cartesian, could be a little bit like you see here, the overall domain. And the processor decomposition is not piece by piece by piece in every Cartesian block, but maybe a couple of blocks together are then tackled by processors. Hence, there's a specific mapping going on that you can see as application scientist. Then we learned an interesting technique, which is already going a little bit towards this advanced techniques, which was about halo and ghost layers. Now you can imagine if you want to have a NWP, numerical weather prediction, as it is basically often done, you would say that each field is influencing the neighboring field when you want to simulate the whole weather, right? In other words, you need the information of the neighbors to calculate your weather in one of the Cartesian block. And this is all nice because in a way you would say, okay, I have lots of cores available, lots of data available, let's do this. But at some point in time, you essentially will face the boundary, right? So as I said earlier, we have distributed memory in the bigger scales. That means I cannot just get to the data. I have to basically receive the data, which stands for these arrows, right? And then, of course, obviously, to help my neighbors, I need to distribute what I have. Hence, I also have to put the data away, what I have, basically for the next time step. So a common modus operandi, called also stencil methods, if you want a little bit, is this T0, T1, where in T0 you compute, and before you end the time step 0, you would exchange with your neighbors all the data, basically getting a receive and then a send, right? In order to have space for it in the domain has some ghost cells that are not really in this nice, beautiful pictures, right? These are more conceptual that you see here, also for the online audience with a red button, sorry, that you see here. These are basically not existing parts of the domains. These are just memory placeholders to get the interaction going, which is the real value of the domain calculated here. It enables us, and you see this beautiful here, that we can actually simulate across the domain, right? Because at the end of every time step, I would exchange the information. And this is the same that is done in many other areas. This is a simulation example from physics. Here is, for instance, a data science example I told you about parallel clustering, where you also cannot fit all the data in the memory. It's too basically hard to do that. So you would crunch the domain in two. Now, normally you would say, why not doing this beautifully here in the middle? Also for the online audience again, maybe it's important to think like sometimes, even if it looks perfect to get the domain basically cut it here between processor 1 and processor 2, here we have to see much more data is in this area, right? Hence more computation. What is one cluster? What is the other? Hence, you would also maybe not always do it so beautifully as we have seen also with tree-based solutions in the last lecture. Then two words which were also incredibly important is the speed up and strong and weak scaling. They are related and also limiting us, right? So speaking first of the relatively speed up, this is important to have strong scaling. You basically always have the same amount of domain that you want to simulate, and you keep that constant, right? The work per processor and per core constant. So here, different examples. Don't get basically carried away by the different colors. Per color, it's still constant. But you see that at some point in time, there's a tail off. That basically means our scaling, which is ideally linearly, so more cores I give, basically the better I have my relatively speed up. But at some point in time, there will be communication problems, load imbalance problems, or what we have discussed a little bit. Now, the other part we discussed is the other way around. Could be, by the way, also I/O bottlenecks, right? Amdahl's law that we had the last time. Then Gustafson's law, if you remember, was a little bit like we in a way don't really want to do just this. We also want to do something which means we want to improve our simulation better, more detail, more granularity. Think about this example. When I do the weather forecast here in this coarse-grained element, on this fine-grained, it will be much more specific. Hence, I could come to a situation where I say, I still have so many cores available, but then I don't keep the work per core constant anymore. Because I have more and more processors, I can actually increase also number of particles per core, right? So having a more complex scenario, more detailed, maybe adding per core then not only the weather, also the interaction with fish and whatever is in the waves, the wave height, all information more and more, so that basically per core you get more and more work to do. And this is a weak scaling. You break basically the application. You would say you could do ever more detail, birds at flying, whatever you put in. And this usually also means that you have at some point in time the weak scaling kind of tail off. But it shows you nicely the efficiency so that you really can, fill maybe the cores, all the memory that they still have to do lots of things to do when there's, of course, a kind of application that really requires it. And that's really the main, kind of terms. They will come more into your blood veins, I think, over the rest of the course and also today. And as I said, this is a more, kind of, really advanced lecture. When you come out of this, you really know how to do MPI programming. Hence, we will talk about several different areas. And if you don't understand everything by heart, don't worry. We have a practical lecture for one where we demonstrate many of this. Especially non-blocking communication versus blocking communication could be a bit tricky sometimes to understand. Then we have communicators, subgroups we will discuss a little bit in the relationship of the neighborhood challenge that is out there, especially if I now want to simulate the Earth, right? So I need to know what right and left is and how I do address them, right? How I do come to them. And then, of course, some elements like network interconnects, which are incredibly important. You understand for the weather forecast, we communicate heavily with our neighbors. If the interconnect is not good enough, then our weather prediction will be very, very slow. The second part of the lecture would be then, focusing not anymore so much on the computation and communication, but rather on data, something we didn't really discuss very much. So how we load data, how we work with data in parallel, what are the bottlenecks of the file systems, how we have a logical versus a physical representation of the HPC systems, and at the end, some data science application examples where we're getting towards standards in HPC, something like HDF. I know if someone of you heard from it, maybe the PhDs, no, hierarchical data format. No, it's a standard in HPC basically to store data in parallel and use it concurrently. And we will talk about it in the second part. And as I said earlier, the learning outcomes is really, with the advanced MPI techniques, you're really ready to engage in real applications. Of course, there's always one API part that I maybe have missed and not talked with you about, but we discuss things like barrier, synchronization, wait all, non-blocking communication, and so on, which all complement what we learned in lecture 2, right? With the MPI basic set, now we go a bit beyond that. And by this also, we see more and more how domain decompositions can be supported, like the Cartesian or subgroups, which you can maybe shape like a tree or like an equal group, it depends on you, and the domain you want to simulate. So really using then HPC systems at scale is possible with the techniques you learned today. So let's get started for a quite interesting MPI lecture. Again, as you remember in lecture 2, I told you we do this in Jülich for 5 days from morning till evening, right? So a proper MPI tutorial would be, much more comprehensive than one university lecture of me can ever carry, but at least it gives the most important parts. Hence, we dive in the elements of distributed memory. Just remember again, shared memory, I can access it, right? The memory space here, I have to always send messages to get data and to access the memory of another processor. That's very important. And what we left out a little bit in lecture 2 as the overview of MPI was then this kind of non-blocking communication. You remember with the ball, I said send and receive. The ball player should be ready to receive the ball if someone is sending the ball. Here in MPI, we have a sort of idea that we can also do this in a non-blocking way. So that in some point in time, I do an MPI receive that you already know. And I always was expecting MPI send to follow, to match it. But what I can do also here is like I do a kind of MPI receive and do a kind of non-blocking send at some point in time. And then I have to do a so-called MPI wait, because at some point in time, I maybe get carried away too much with my application logic so that I wait for the other processors. Hence, there's a synchronization element in it, which also causes here and there, let's say, imbalance. Right here, a late sender problem maybe. And of course, when you have the trivial case, right, you see this here optimization patterns. Sometimes people do exactly this. They have an ICE and immediately an MPI wait. That is, for instance, an example where you can do directly an MPI send. This only pays off if you have some certain logic in between that you can just do alone, while you're basically waiting then at some point in time for the other one, because in the bigger applications, it could be quite some time step that you see a little bit here, where the other one is not directly synchronous working on the same application, right? This was entering receive quite some time ago. And then some point in time, this kind of non-blocking communication kicks in. There's a whole performance analysis paradigm to it where you can identify some of the wrong programming. We basically have removed that from the course at some point in time because it's, firstly, more modern topic like GPUs came, deep learning came, AI came. And secondly, there are, let's say, big programs which today have some tooling like Scalaska, where you can run them, instrument your code, and then you identify those problems. Hence, for us now, it's more important to get the message that Not everything needs to be always like MPI send receive. You have some of them are really non-blocking and do several things. And new for you is a little bit this wait element where you wait for certain MPI requests to finish and then continue in the application logic so that you can synchronize a little bit processor name and wall times, these small helper tools, and all of that is part of the MPI API as well. So hence, and that is almost what I already presented to you here in this element, the blocking communication is quite, often used. Immediately when you come to non-blocking communication, it's getting more tricky, everything, the whole program logic. However, it enables you that you maybe can do more work per processor. If you have, let's say, a certain load imbalance, you can maybe do some work. But it could be really leading to performance problems, as I said here. Essentially, what you see here is a waiting time for this processor down here. And that's bad, right? It enters the MPI receive. Nothing happens, right? Which is bad for the processor. Just waiting for an MPI function, nothing comes. Hence, ideally, that would be, of course, here. But that's not the case. And exactly to find these patterns, that's why I use performance analysis tools, right? So this is one of the elements to take away. And you see in other areas, it's the same idea. When I have I receive a non-blocking communication and do a wait. And then this is again a waiting time. And you find many different examples. If you go to the metrics tool here in the references, there are around 20 performance programs that you have. And the benefits that you sometimes have is you can avoid some deadlocks that you program in terms of wait, and then what you usually would have that another processor will maybe never add it if you have ranks, which ifs, else's, and so on, which is really quite tough to understand. But yeah, this is something which is just another set in your tooling of APIs to use. And let's consider as an application example. You would say, what happens now if I do this to our neighbors, right? I want to do this. I want to have maybe an I send receive, and I send 4 times, as I said, spread out my data. I receive, get the data from my neighbors while they do their old physics calculations and so on. This is all nice. Then I have, for each of them, I can edit requests in, right? It's an MPI status request that I can put in the API. No worries, we'll have some examples in lecture 4.1, right? So it's just the first conceptual ideas. You wait for all of them, a new API function, and that's all beautiful. Now, what is the trouble here? The neighborhood, right? Now, when we think about doing this, how in the world should I know, almost literally in this world, and coming back to our real world, MPI.com world, how are my neighbors and where are my neighbors, right? What ranks do they have? I basically have to manage that on my own if I want. I mean, I could do this and say, I do my own Cartesian or so and would say, assign it just and say, you're always starting with 0, 1, 2, 3, 4. But of course, this means at any time when you do an up-down, let's say, or your neighborhood communication in a loop, right? Because we do it, of course, with 4 neighbors. And then you think about that this is executed for all of the different cells, right? Multiple programs. We basically have to do lots of management of this Cartesian coordinate. Hence, you see where I'm alluding to. The new communicator may be quite nice, which gives us then the question, or the answer to the question, what are now the cores and tasks in my neighborhood? So they can address them for a send and receive. Because I need to know destination and source in my MPI, right? I still have to do the messages. But this is something what we miss in the moment. We don't know in MPI.com world who is really next to me. And what I also will present with the Cartesian now, which is the motivator behind this, is even if this is an ideal world and we now say, okay, we break that up into different subgroups, it will be never that also the physical system will be like this. So what I explain you with the communicator is more a conceptual logic idea. And there will be some processing underneath, but at least it gives you a way of tackling these communicator and tasks that are closely located as groups, like you see here. And there are different ways how you can do it. One important one, which is a very trivial or simple one, is the MPI com split. So you see still starting as com world. As we discussed before, we can do it in 2 groups and split it. And then also we can here do it in a kind of layered way. For instance, this would be MPI com world. And then I would say after each or after 4 rungs, I will create a new subgroup. And that's how I split this communicator. Important is that I now basically have this 0 twice, right? Now there are 2 ranks with having 0, or here the same way. Here I have 4 ranks 0. Why? Because I'm now part of a specific other communicator that I created, right? In a different group. Otherwise I would be not unique anymore. So per group, I get a new rank. This is important to understand, while I still maintain my overall unique rank in MPI com world. Again, that's maybe not directly obvious from the slides, I know. That's why we have also some practicals afterwards, including this presentation where you have now the same idea we already know, init and finalize for MPI. You know that already. Then I have com size, com rank in com world, our overall course. And now I can split this MPI com world, maybe like the color that I said here, the color coding, like after 4 ranks, I will start a new group. That is basically what you've seen here in the next couple of things with the com size. I get then the row communicator, which is now a new communicator, which I created here, and that exists in parallel. You can always use Volt. You can always use a row now. And for different, scientific problems, whatever you want to do, this might be useful to do. Hence, especially for the Cartesian, but this is already a next level, a next communicator. So this is just a row-based one, very simple for some of the problems that we defined by 4. Nobody said this needs to be like this. We could do also 8, maybe. It's just an example. And working then with these communicators enables us to do quite some nice application logic. You could say that one part of the group is, as I said earlier already, the ship movement. Others will concentrate on the waves, basically, that are on this kind of, different, river parts and so on. And this is a quite nice tool that you can have, right? So it answers a little bit already the question to what we say here. The neighborhood is then given by these different ranks that I have in the different communicators. And now creating one that is our world, that this would be, of course, another idea when you think about the bigger picture. Here we had maybe with groups, we can do this. But when you have now also interact in the whole grid, then the group-wise fashion and so on in one direction or something like this doesn't really make sense. Hence, there's a Cartesian communicator to the rescue. There's a complete command called MPI card create, where you create a completely new communicator out of this MPI com world. A view how to see that, and here are different grids. You see here 16 processors. Here we have 12. That is something what you now can create. You can create a 3x4. You can create a 4x4 Cartesian grid. Obviously, if you have the whole ocean, you probably create a much, much bigger size of that. So this is still to capture the essence or the kind of conceptual idea of the Cartesian communicator. You would still maintain your ranks in this Cartesian communicator. And on top of it, everybody has a Cartesian coordinate, what you see basically in the way below. Now, the interesting thing is now the MPI will give us a way to get my neighbors. So when I want to do a send and receive, I am able to know that basically just asking the MPI environment, when I want to go down, what is basically my communicator in the destination when I send. It's the 8. So that's something what I get here, which I otherwise would never know, right? And the same is true basically for the source. When I get information, let's say I'm somewhere here in this ocean part, from who I get information, because I have to do a receive with the source. And then basically people will say, okay, I get my source from 0, which is this. Now, obviously, this depends on the paradigm, how you shift. You can shift in this direction, shift in that direction, up, down, left, right, and so on. Hence, you will have, of course, for these different operations where you indicate the step now of the shift. Important for you in the head is the shift doesn't do anything. Once again, the shift doesn't do anything. That's a bit confusing. I know why, but I told you that there's no send and receive. That's the most problem that sometimes students miss with this, also in exams. I mean, we have a final project, so you maybe not run into this. The shift is just preparing the data exchange. The real data exchange is send receive still. But the shifts will basically know, okay, that is where we get the source and destination of the processes. Also, this will be explained a little bit on the next practical lecture where I demonstrate this all. Here is a small communicator that we have just seen created. With MPI World, I say the dimensions, which is an array 3 times 4, no surprise there. And I do the coordinates, I get them. So I now have the coordinates of the Cartesian. And as you see here, we Cartesian shift, that's the command for it, just in order to understand the source and destination. Again, nothing, no data sent. Then I start my MPI send receive and do a real exchange to destination or getting a kind of source. This is a send receive command, once basically both in one. Any question on that, or that's understood? Yep, here in front. I repeat for the online audience. There's a question how you indicate now basically the direction of the shift, right, so to speak, which essentially is kind of in this element here. We will play around this a bit more in the practicals, but you can indicate which step size and which direction you want to do. So it's part of this kind of shift to indicate now where you want to go. That's a good question. There was another question at the end. Okay, I try to get this in line. So the first question was really for the Cartesian creator to think about. I'll take it to 3D first. So the 3D is possible. In the reality, you would come, however, to a point that you have a multidimensional part, because in each of the different blocks of the domain you want to have in 3D, you would have lots of physical domain variables you also want to capture, right? So let's say the amount of fish. You have another dimension, so to speak, to think about. In this sense, this is supported. So these are simplified views on it. And I think I have a demo on this practical lecture 4.1 also for this part. And the, yeah, what was the first question again? Sorry. Yeah. Okay, sorry, I dropped that. Now, the first question that was also part here raised was how big can be the dimensions? And of course, this is a loaded question. It depends on memory of your computer. Theoretically, it could be very large, but it has also to do with your core mappings, with your task mappings, because each of these different dimensions will be mapped to tasks. And if you don't have enough processors available, it also will fail. I will do a demo on this. For instance, if it mismatches your job script, you would say, I asked for 11 tasks, but have 12, there will be a problem in the MPI environment. So it's a good element. It's not too simple to answer because it depends. It has many relationships also with your job script, how much tasks and cores you have available. But good question. Good, so let's continue a little bit. As I said, also, it's a little bit more better view when you have the practical lecture aside, so practical 4.1. And of course, these things are also one part of a potential final project you can do. It's called the fishing simulation. This is one opportunity that you have. There are different ways of a final project that you can do. You don't have to do it, but if you do this fishing simulation, then you would be dealing with a Cartesian much more. Now, coming to some other communication elements, with something we left out also is synchronization, which is important. For instance, here, the collective operation. If you think about that, you want to maybe have one rank storing all the results to file, and another is doing something else. Here, the sleep command, not so important, but you see already in a way to properly finish this program, both of them have to finish. You can do an MPI barrier of MPI World, so everybody will reach this barrier. And then basically the computing will be stopped here. This is, of course, lots of load imbalance problems potentially, right? If you think about, you would have rank 0 does nothing, and rank 1 takes now an hour to store everything to file. Rank 0 has nothing to do and waits for an hour in MPI World. Also bad, right? So it's idle. That's what we don't want to have. Hence, the synchronization barriers you have to do with cautious. Many performance problems are related to it. It is nice for our human mind to have and to use them. Another element that we didn't really touch in was to shift the view a little bit. So we talked a little bit about computation all the time, but think about that there are also bottlenecks and load imbalance problems if it comes to the network. The network means how we interconnect all this cores is incredibly important too, for throughput of many, many interactions. You could have a mesh setup, a tree setup, and we go quickly a little bit into that. You don't need to know all of that by heart, but it's something which, of course, you also have to understand. It's not only computing or memory, it's also the way how you basically access files or how you basically interact with each another. Here you see an example of one mesh where you basically have also very dedicated nodes even for I/O, right? So I/O nodes, that means if you want to store something to file, you always, let's say from this processor here for the online audience, when I want to process here and drop something to file, I just cannot do this. I have to go via the I/O node. With this, I communicate through many other connections to reach I/O and store it. Hence, another load imbalance problem that you maybe have in your application. And hence, we will talk later about parallel I/O and elements, right? Usually you see a little bit here, this bottleneck of switches. So you have many compute nodes, and as the cable connections are one of the most expensive part of the HPC application, the cables. Every core is every core. You can imagine this is something where people don't do that anymore and have, let's say, other topologies they try to do there. So the fully connected mesh is, let's say, something which was often there, but nowadays people do much more, let's say, trees or even dragonfly networks. This is just a little bit about diameter, which is the shortest distance from the most far away elements. And you can imagine that we need lots of switches on the way to connect really a big systems that we have. Coming to a concrete example, this would be something where you have different switches and every core is still nicely connected to everyone, right? So with full performance, you can get to every other that is basically here. So we call that a fat tree. Fat tree implementation, every cable connection with the switches is connected somehow to the other one. Very expensive, so rarely used in practice because the cable connection, again, InfiniBand is one of the most important parts. Of course, on the other hand, the applications are very happy, right? Of course, the applications have perfect performance, but it shows also in practice that we don't need this all the time, right? And this brings us to something we call an oversubscribed tree, where you see we lose a little bit one of the connections here and lots of cables to assume that maybe there's lots of regional computation. And I could talk about this for 2 or 3 university lectures, especially as there's a new topology coming in called Dragonfly there. I think here in the course, it's a little bit just showing you that these network topologies are there, but they're also performance related. So here to communicate with another one has always maybe a bottleneck that 2 others may be already using this connection. There's an oversubscription that is not fixed. It can be varied from different systems. Also here you see the Dragonfly, just as a side remark, alone this would be probably 1 hour talking about in detail how that works. Just assume that you have a regional element of communication, and this regional island, so to speak, are still very good connected to other elements of this. I have an example of a real Joule system later on where you see that a little bit. Hence, you sort of still have a very good throughput of your application. If you assume regional communication, what many of the applications do, if you now think about the weather forecast, you have your regional elements where the weather is influencing. Let's say you have a climate study of the whole world. Chances are that one element which is in the region will communicate is much higher. If you have another complete different region, chances are that you don't need to communicate so much with this region, which is far, far away, right? So this is something where Dragonfly and new topologies come in, especially as we now have exascale, right? Now we have a small mesh in the past and a couple of processors, a couple of racks. Now when we really approach exascale with different cluster modules and booster modules, if you remember about modular supercomputing, I gave you the example. And you have here one of a real system, the Joule's booster module, if you remember GPUs and so on. But of course, we have some applications that should connect to the Jewel's cluster module, right? For real computation on CPUs. Now, in order to achieve that, you have this dragonfly again, that you have all these different booster nodes, which sort of have regional networks very strong and still are very connected with the other parts, and still are able to, via this kind of special nodes and switches, then to come to the cluster node. Again, favoring a bit this kind of top level connection, which assumes regional computation. Another interesting thing is to look a bit on the chip and to see a node card now, where now we are in the position after some lectures now that to understand a complete different node card that is existing in reality, right? You see a little bit, it's hard for the audience here. These are A100 cards from NVIDIA, 4, right? They're basically in one node. Then you have here PCI switches that connects nicely to the host CPU, right? We're talking now multi-core CPU versus many-core GPU, if you remember. 2 different things. And now we see also nicely that, of course, in order to go now outside the node, right? Outside this, we have this kind of connection, which we just discussed with this. So that every one of these nodes is one part here of this dragonfly booster, is connected to all of the others, and then basically can also go to the cluster, which was more CPU intensive, right? So this is a real life system existing with many, many cores. You see here it's just 4 CUDA cores or 4 CUDA cards. And we have here 6,912 in the overall system, following this topology of the connection and architecture, if you want. So I have always a certain node architecture, and then also the overall architecture, how you connect the nodes. And this both is basically also a little bit affecting the performance of the system. And I guess that's all what I have in this first part of the lecture for you. To understand a bit more InfiniBand, the connections between the different CPUs and GPUs these days, I brought you a little bit of video that I'll play in the break. So we continue with part 2 in 10 minutes.